Hey there, calculus fans. Here I'm just going to give several proofs of the derivative of e to x and just talk about it and see where that takes us. You do want to watch my previous video on where e comes from, that it comes from this study of compound interest, and that this is what I get. That's a different discussion. We need to take that as given. If you want, you can watch my video on the derivative of log. There are ways to get the derivative of log kind of more naturally follows from this, and you get this, the derivative of the natural log is 1 over x. So that's why a lot of, more technical proof books start with the log, because it's easier to prove the derivative of the log and then use that to prove other things about e to the x. So you could also watch that video. If you do know the derivative of log, then you can write, and you want to work with e to the x, you can do the following. You can say, okay, I know this. I can rewrite this as x equals the natural log of y, and then differentiate both sides with respect to x. Now that's this idea of, you can't do that unless you know implicit differentiation, so this is not for everybody. It depends on the course you're in. But then you can take the derivative using the rule you already know, times dy dx. And that's often the way it is when you have two functions, one that's the inverse to the other. You find whichever one is easier to take the derivative of or to prove, and then you use that to prove the other one. So from this, you get dy dx has to be y, and y is e to the x. So I kind of like that proof, but that requires we know e to the x. And I would like to show, so there's the proof using we know what the derivative of the log is. All right, so let's get rid of that. Let's go to first principles. And that's what I have down here. So if you know, I'm going to talk about a to the x, a more general version, assume a is some positive number. Ultimately, I'd like to plug in e here. And over here on the right, you can see the proof I casually give to my business math class, because there's no proofs in that class, so I'm just trying to give some. I try to include everything in there about the fact that e is this special number. But I sort of don't know that I like that proof. It's just a throwaway comment on the side of a page. But here's a little more formally. So if someone gives you this, you can realize that you can factor out a to the x and rewrite it this way. Now, if you're trying to make this appear, it takes a little bit of cleverness. One way to do it is to replace the top with y. You could also, a lot of people, if you look up a proof on this, they will just quote this fact, that this is the same as the natural log of a. But that part is not obvious to me, so I don't want to make a quote of this fact. So anyways, that gets this. You solve, you get this, and then you can write, and it's a clever little bit of maneuver. I think no matter how you do this, you have to do something like this. But you can write this, it's kind of like writing 4 as 1 over 1/4. Yeah, I know it's weird, but it's okay. That's what I'm doing. I'm writing y as 1 over 1 over y. Why am I doing that? Because I'm hoping I can make this expression appear in some sort of way. Okay, so we have the log base a, and then you can write this. And ultimately, I'd like to take the limit as h goes to 0 here. Now, as h goes to 0, y is also going to go to 0. Okay, so here's the key step, is we can write log base a, and then in here we can write y plus 1 to the 1 over y. Now that doesn't look exactly like this, but very similar. So if you replace 1 over y with n, or y with 1 over n, then you get the same thing. So now let's do it. We want the limit as h goes to 0, so that means y goes to 0, of this thing, a to the x times 1 over log base a of this thing, 1 plus y to the 1 over y. And that's finally where this pops up. Okay. So then what are we going to say? Well, this piece in here, where does it go when y goes to 0? Or if you prefer, replace 1 over y with n, and n is going to infinity, as long as y is approaching 0 from the right. So anyways, this approaches e. And so our final answer is a to the x, 1 log base a of e. But that's the same as a to the x natural log of a over natural log of e. And so it's a to the x times the natural log of a. And in particular, if a can be this special number e, it then just becomes e to the x. I was going to show some visuals on this way of thinking about it, so let's look at that. So here on the left, you can see b to the x. B is the base. So right, like if I make b 1, it's just a line. You can even make it negative. And I've drawn the tangent line, and over here I've drawn the derivative, which gives the slope. Okay, so let's look at a positive value of b, like b is 2. So this is b to the x. The value would be 1.189. So an interesting thing is we're really looking for when is the derivative as nice as possible. Or in other words, when is the slope the same as the y value? Now at this point the slope is 0.82 and the height is 1.18. So it's not quite the same. So if I increase this a little bit, go to like 2.5, you can see that the height is 1.25 and the slope is 1.15. They're pretty close to the same. Now if I go way past, they're not the same again. But there was a moment when they passed each other. And this was at this 6.7. 6.7, the height is a little bigger than the slope. At 6.8, the slope is a little bigger than the height. So there's some sort of balancing point in between. Now you can keep fine-tuning it, and I don't know that it allows me to do it much finer, but if you can get to 2.71, they're even closer. And then 2.718, they're even closer. 2.7182, they're even closer. 2.71828182, that's as far as I can remember. Then they match up very closely. So it is this special value when that comes out. So let's go back to the proof. E is this special value that makes this limit right here go to 1. And if it goes to 1, then the derivative of e to the x is just e to the x. So there you go. There's several different perspectives of this rule that many students know well from calculus, which is that the derivative of e to the x is e to the x. Now, if someone hands me the function 5 to the x and I have to take a derivative, there is a rule for that, but if you ever forget, there's a clever little way to always make the base e. And that is to basically take any number you want and write it as e to the log of 5. So this would become log of 5, all raised to the x power, but that just means times x. And then if you're comfortable with the chain rule, you can take the derivative. So using the chain rule, the derivative is itself times the derivative of the inside, which is the log of 5. And then if you want, you can rewrite this as 5 to the x times the log of 5. So in general, the rule is there's these two rules. The derivative of e to the x is e to the x, and the derivative of a to the x is a to the x times the log of a. All right, I think that's enough of that. Hope you found that interesting.